What if I told you there's an idea, all the way from 1976, that can actually predict which parts of your favorite app are the most likely to crash? Well, there is. Today, we're going to dive into a groundbreaking paper by Thomas McCabe that literally gave us a way to see, measure, and, most importantly, control the hidden chaos lurking inside our code. And it all kicks off with this question that sounds so simple, right? How complex is a program? But back in the early days of software, this was a massive blind spot. I mean, think about it. You had engineers building these incredible digital skyscrapers, but they had no way to really inspect the foundation. How could you possibly know if what you were building was solid or just a house of cards waiting for the slightest breeze to knock it all down? Okay, to really wrap our heads around the scale of this problem, just look at this number. 33,554,432. What in the world could that possibly be? Get this. That is the number of possible paths through a tiny 50-line program. We're talking about a program with just 25 simple if-then statements. That's it. And suddenly, that shocking reality made one thing crystal clear. The old way of thinking, just counting lines of code to measure complexity, it wasn't just wrong, it was completely, hopelessly inadequate. So how in the world did McCabe even begin to tackle this chaos? Well, here's our game plan. We're going to see why just counting lines wasn't enough. Then we'll get into his brilliant idea of drawing a map of the code. We'll discover the magic number he came up with, learn what makes code go all spaghetti, and finally, we'll see why this whole thing still matters so much today. Okay, so let's set the scene. We're back in the 1970s. Software is starting to run pretty much everything. We're talking banks, power grids, you name it. But here's the problem. The engineers were basically flying blind. They had no reliable way to find the ticking time bombs hidden in their own systems. Those specific parts of the code that were going to be an absolute nightmare to test and just suck up all the money and time. And McCabe, well, he put it perfectly right there in the paper. This idea of just limiting programs by their physical size, like saying, hey, no module can be over 50 lines long, he flat out said, this technique is not adequate. And we just saw why, right? A tiny program can hide a truly mind-boggling amount of complexity. So what was the big breakthrough? Well, here was McCabe's genius move. He realized everyone needed to stop reading code like it's a novel, line by line from top to bottom. Instead, he said, we need to look at it like a map, a visual guide to its actual internal logic. And this map has a name. It's called a control flow graph. The easiest way to think about it is like a city map. Seriously. The blocks of code, those are the buildings. And the arrows showing the flow, those are the streets connecting everything. All of a sudden, you could see the program structure. You weren't just reading it anymore. And that was an absolute game changer. And this slide just illustrates the idea perfectly. So on the left, you've got your standard everyday if-then-else statement. But look at the right. You can see exactly how that logic translates into a simple diamond-shaped map. This invisible decision-making process, it suddenly becomes a real, tangible shape that you can look at and analyze. Okay, so here's the cool part. Once you have a map, you can start to measure it. And this is where McCabe introduces his big idea, a single powerful number to actually quantify the complexity you're seeing in these graphs. It's called cyclomatic complexity. Now, I know the name sounds kind of intimidating, right? Cyclomatic complexity. But the basic way to calculate it is unbelievably simple. Seriously, you just count the number of decision points in your code, your ifs, your whiles, and then you add 1. That's it. And why add 1? Well, that just accounts for the one single path through the code if there are no decisions at all. And boom, that's your complexity score. But wait, there's an even more intuitive shortcut, especially if you have the map right in front of you. You can literally just count the number of enclosed regions on the graph. So for this one here, you can clearly see 1, 2, 3, 4, 5 distinct areas. So the complexity is 5. It's so simple, so visual, and just really powerful. Now, of course, these simple little shortcuts are all backed up by some pretty serious math, specifically graph theory. The formal equation, and don't worry, you don't need to memorize this, is right here. It's all about edges, nodes, and components. Think of this as the heavy-duty engine under the hood that makes all the simple tricks work. But this wasn't just some abstract academic exercise, That's what's so important here. McCabe didn't just give us a theoretical number. He gave actual programmers, people working on real projects, a practical, actionable target to aim for. And here it is. This is really the aha moment of the whole paper. When McCabe went and analyzed real-world code, he found a direct, undeniable link. The higher a module's complexity score was, the more bugs it had. Period. So this number wasn't just some abstract math concept anymore. It was a predictor of actual, real-world pain for developers and users. So based on all this data, McCabe proposed his now famous rule of thumb. You should try to keep the complexity score of any given module under 10. And you can see the difference right here. On the left, you have a nice, simple module with a score of 3. The map is clean, it's easy to follow, but on the right, at a score of 10, it's already starting to look like a tangled web. And his point was, anything beyond that, you're just asking for trouble. So what happens when you blow past that limit of 10? Well, McCabe's whole visual approach also gave us a super precise way to define every programmer's worst nightmare: spaghetti code. He actually identified 4 specific forbidden patterns you could see on the control flow graph. Let's go back to our city map analogy. Think of these as making illegal U-turns or driving the wrong way down a one-way street. We're talking about things like branching into the middle of a loop from the outside, or jumping out of a decision block in a weird way. These are the kinds of moves that create logic that's just confusing and totally unpredictable. And here they are, visually. These are the signatures of spaghetti code. By pointing out these very specific, forbidden shapes, McCabe basically gave programmers a visual checklist of what not to do if they wanted to keep their code clean, structured, and understandable. So you might be wondering, why are we still talking about a paper from the disco era? Well, it's because its impact is literally woven into the fabric of just about every piece of software we use today. This paper really represents a fundamental shift in thinking. We went from a totally superficial measure, like the physical size of the code, to a deep structural measure of its logical complexity. We stopped judging code by how long it was, and we started judging it by how tangled its decision-making map looked. And maybe its most practical legacy, the thing that's used every single day, is in software testing. That complexity number, it's not just some random score. It tells you the exact minimum number of tests you have to write to make sure you've covered every single possible path through that piece of code. It gives the testing team a real, concrete target to aim for. Which brings us to one last thought to leave you with. McCabe gave us this amazing tool to manage complexity when programs were measured in the thousands of lines. Today, our systems have billions of lines of code. So, as software keeps eating the world, the real question is, how do we use these foundational ideas to stop its overwhelming complexity from eating us?